bubble dynamic in nonlinear encapsulated shell. I'll start by a brief introduction about acoustic droplet vaporization and its applications, and then we will review the model and some simulation results. Droplets that are composed of specific materials are stable at the body temperature and atmospheric pressure, but if they are exposed to acoustic wave, their stability is disrupted, phase change from liquid to gas happens, and this process is called acoustic droplet vaporization. Why we are interested in studying the ADV process? Because it has many applications in the field of medicine. They can be used as contrast agents in acoustic imaging. They are very good candidate for drug delivery, especially for delivering drug to a specific location without disturbing the surrounding environment. They can also be used in tumor treatment to embolotherapy and histotrypsy. So that's why we like to explore in more details of what's happening exactly in this process. One important factor in studying ADV is calculating or determining the minimum acoustic pressure that's required for direct vaporization. This is called the direct vaporization threshold or ADV threshold. Several mathematical and experimental models and studies have been done so far to determine ADV threshold under different environmental and mechanical conditions. From the theoretical aspects, at the beginning, the focus of most models were assuming that droplet is immersed in an infinite liquid. This is not a good assumption because we know that usually droplets are encapsulated by shells, which give them more stability and on the other hand makes the process more complicated. Models were modified later by assuming that droplets are basically covered by linear elastic shells. So the coating material is composed of linear elastic materials. And again, this is not a good assumption because we know that large deformation happens in ADV process. So basically linear elasticity cannot capture this large deformation. This assumption was relaxed later by assuming that shell is basically composed of non-linear elastic material here that can describe large deformation observed in this process. So what's missing here and what we wanted to do? We know that bubble grows in the exposure of acoustic wave, but this is not always happening. Depending on acoustic amplitude and frequency, they can collapse as well. When bubble collapses, although the process is very fast, but temperature and pressure of bubble significantly increases. They exceed the critical value and bubble basically enters supercritical state that needs to be described accurately. And this is actually our objective. We wanted to develop, let's say, a mathematical model that can describe a bubble dynamic encapsulated by a nonlinear elastic shell, and also describe the supercritical state happens after bubble collapse. This is what we wanted to do. For this purpose, we define our computational domain as a four-phase system. It's composed of bubble with radius RB, which is nucleated in the center of the droplet. And these two are encapsulated by a thin shell and with R1 and R2 as the inner and outer radius. And this three-phase system is immersed in a liquid phase, in a water, let's say. To build a model, we made some assumptions. We assume that symmetry and a spherical shape of the system is preserved during the simulation. There is no mass flux at the shell interface because time scale between evaporation and the mass diffusion are different. So obviously this makes sense. And also for more accurate description, and by more accurate, I mean to have a better agreement with experimental data, we assume that gas inside the bubble is van der Waals gas instead of an ideal gas. Many equations are involved. I'm not going through all of those equations, so just a very quick review that of course we need a van der Waals equation, and we also need the mass flux because of evaporation and condensation at the bubble interface, which is defined by J here. And the base of our model is a kind of Rayleigh-Plus type equation. So it can be obtained by integrating a momentum equation over our computational domain. And this is the final equation that we have here. Some terms are involved. Again, I'm not going to explain all these terms in detail, but the important one here is PR, sorry. So this is PR. So here in the first, that depends, this is the pressure at the bubble interface. It depends on the bubble pressure, effective surface tension, effective viscosity, and two more terms that I will explain shortly. So psi here is the contribution of mass flux, depends on J, and J needs is basically proportional to temperature derivative at the bubble surface. So obviously we need to have heat equation for our system. Bubble interface is not stationary, it moves because it grows. So we define a moving coordinate as psi equals R minus RB. And by these coordinates, we have heat equation in this form with appropriate boundary condition at the bubble surface and an infinity. So the last term in the PR equation is S, which is basically important. This is elastic response in our model. As I said, to capture large deformation, we need, we assume that bubble is encapsulated by a nonlinear elastic shell that follows Mooney-Revlin equation. After some substitution, some simplifications, we end up with this equation for elastic response S. Here, G is the linear shear modulus, and beta is a fitting parameter on nonlinear coefficients, let's say. These are R10 and 20 are the initial radius of shell, and R2 can be found by this equation because of incompressibility of shell. As I said, beta is a nonlinear coefficient. In the Mooney-Revlin equation, we don't have stress-strain relation. What we have is energy density function. To make this function positive, beta needs to be between -1 and 1. And the response as a function of displacement shows that basically the process is smooth if beta gets closer to 1. So we can say that beta equals 1 basically optimizes the process and corresponds to a soft shell that encapsulates the droplet. These are needed to be coupled with the three more differential equations. One is for the bubble density, another one is for the radius, inner radius of the bubble, and the last one is for the temperature of the bubble. Temperature of the bubble can be found by pressure, differential equation for pressure, and the Clausius-Clapeyron equation. And if everything is found correctly, then we can use a van der Waals equation to calculate bubble pressure. These are all good as long as a collapse does not happen and bubble remains far from the supercritical state. What we should do here after bubble collapse, this is actually what we wanted to do. And since this application is usually in the field of medicine, we need high precision and more accurate description as much as possible. So at this stage, when collapse happens and bubble reaches the minimum radius, there isn't any interface between liquid and bubble. So basically J is 0. And we can assume that bubble enters an isentropic process. So to describe the variation of bubble state, we can use the isentropic equation, which is defined by this equation. So by this equation, it can relate pressure and temperature, bubble and temperature and pressure of the bubble. And here we have a parameter gamma. Gamma needs to be calculated for this process. And of course, it depends on the derivative of bubble density with respect to temperature. We use the van der Waals equation for taking the derivative and did the substitution. And here is what we have for gamma, sorry. Here is what we have for gamma. So now we have two states. As long as bubble does not collapse, then everything can be followed as I showed you, and we can use van der Waals equation to calculate bubble pressure. But when bubble density exceeds the critical value and it enters the supercritical state, then we can use the modified equation to calculate bubble pressure. So that was the overview of math, what we did. And now let's review a few simulation results. The first key factor in ADV process is acoustic amplitude. Here we have bubble radius as a function of time for different values of amplitude for two cases. In panel A, we have the results for beta 1, and in panel B, we have the results for -1. Remember that beta 1 corresponds to the optimized situation for evaporation. What's happening here? So you see that the minimum value is shown, that the results for the minimum amplitude is shown by the black line. At the beginning, when we are in the negative cycle of acoustic wave, pressure inside the bubble is more, so it increases until we are in the positive cycle, and then inward pressure increases, so bubble radius decreases. It reaches the minimum value here, and then there is enough pressure to counterbalance the inward pressure, and then it increases again until complete evaporation. So at this stage, droplet radius is basically 0, and we have a complete vaporization. However, with some bounce, this is not what we need. We want to have direct vaporization for some optimum situation. If we increase A, the acoustic amplitude, you see that direct vaporization happens without any bounce. And this is basically the ideal case. However, it needs to be modified. When beta changes is changed to -1, as I said, we have kind of a hard shell, so it's not the optimum case for evaporation. You can see that for the minimum value of A, which is shown by the black line, evaporation does not happen. We have some oscillatory behavior, and at the end, simulation is terminated. But by increasing acoustic amplitude, evaporation happens, however, with some bouncing behavior. And we have direct vaporization only for the maximum pressure. The next determining factor here is shell elasticity. Of course, material is important here, and we wanted to optimize the process as much as possible. To see how it affects the process, again, we have bubble radius as a function of time for different values of G. It goes from 20, softest case, to 320, hardest case. And in A, we have the results for 1. You see that for the softest case, direct vaporization happens, which is good. By increasing G to 120, it happens still after one bouncing. And for the largest value, we don't have any evaporation here. So we have just collapse. And this is not good. And for -1, for beta -1 in panel B, the situation is even worse, because we have vaporization only for G20, but not direct vaporization. And if you can see here, you can see here in the temperature results that when we have here, the dashed line shows the ambient temperature and the critical temperature after non-dimensionalization. During the evaporation process, temperature is below the T infinity, the ambient pressure, everything is safe, good. As long as collapse happens, we have huge increase, significant change in the temperature, that's better to be avoided. So, and as I said, since the bubble enters the supercritical states, it needs to be described correctly. As I mentioned, an important factor in a studying ADV process is determining the threshold, the minimum pressure required for direct vaporization. Here we have the results for threshold as a function of frequency for different values of G. You can see that in the range of no frequency, material is not a determining factor. So when frequency increases, pressure decreases, so all good. It reaches some optimum value, and then depending on the material of shell, by increasing frequency, direct vaporization threshold also increases. And it's more significant when the shell is hard. So depending on the application, range of frequency that we are working with, so we can adjust the frequency or the shell material to have minimum threshold here. One more thing that's good to know, G0 here is in a kind of extreme case. And you see that we have the optimum value for G0. This basically shows that besides shell elasticity, droplet size is also an important factor, the total or the finite size of droplet that should be vaporized. And the last thing that I want to mention, and that's good to know, is about nucleation time. In many theoretical studies, it's assumed that bubble is already nucleated at the initial time when we apply acoustic vapor. This is not pretty correct assumption. We know that bubble nucleation happens in the negative cycle of acoustic wave, but not necessarily at 0 unless pressure is so high. And also, temperature continuity is not preserved by this assumption. To address this question, we have the Laplace pressure, the initial Laplace pressure for the bubble by this equation. We can assume that initially temperature of the bubble is T infinity. So we have balance or continuity of the temperature. It gives us the initial value for bubble pressure. If we know the bubble pressure, we know the amplitude, we know the frequency, then we can determine nucleation time. This is basically the time that bubble starts growing and inflates the droplet. And this is not necessarily zero. And we will see that it basically affects the results because two supporting things are working together. So you can see here that if we calculate the nucleation time and acoustic wave is applied at the correct time with the correct phase, lower amplitude is required for direct vaporization compared to the previous case. You see that we have direct vaporization for 0.6, which is much smaller than the previous simulation. And for the direct vaporization also, you can see that there isn't that kind of increasing behavior. In the range of low frequency, it's happening at the lower pressure, much smaller than the previous case because nucleation time is far from zero in this case. But in the range of high frequency, this is pretty close to the previous case when nucleation time is at zero, because again, nucleation time and zero are kind of close together. So that's the end of the simulation. And here is a summary. What we did was basically developing a Rayleigh-Plessa-based equation to describe bubble dynamics and ADV process and considering the large deformation happening in this process. We actually showed, and the emphasis of our study was correct description of supercritical state that happens after bubble collapse. We showed that shear modulus, or the material of shell, nucleation time, and the radius of droplet are important factors here that need to be considered. And for theoretical study, there is one thing that's good to know. I didn't show you the results, but usually it's assumed that simulation is terminated when shell thickness is very thin. Mathematically, we can set it to very small value, but physically it's not possible. We showed that to capture complete vaporization, it's important to set up the initial thickness to an appropriate value. Otherwise, simulation is terminated before capturing the complete vaporization, and it can cause some over or underestimation comparing to experimental results. So that was good to know. And that's it. Thank you very much.
Okay, thank you very much.